Imagine a celestial object so dense, a single teaspoon of its material would weigh as much as an elephant on Earth. A cosmic diamond, glittering in the darkness, the incandescent heart of a long-dead star. This isn't science fiction. This is the reality of a white dwarf. For billions of years, stars like our own sun blaze with nuclear fire, fusing hydrogen into helium, then helium into carbon and oxygen. But this fiery dance is finite. Eventually, the fuel runs out. The star exhausts its nuclear furnace, and its outer layers are gently puffed away, creating breathtaking planetary nebulae. What remains is the star's core, a supercompressed ember, the white dwarf. These stellar corpses are among the most common objects in the Milky Way, yet their true nature is a testament to the bizarre and powerful laws governing the universe. They are the silent witnesses to cosmic history, the final act in the lives of stars, and hold clues to the ultimate fate of our own sun. Let's journey into the heart of these stellar embers and uncover the profound physics that make them so extraordinary. The birth of a white dwarf begins not with a bang, but with a slow, inevitable fade. Our sun, for instance, is currently in its main sequence phase, a stable period lasting roughly 10 billion years. It's diligently fusing hydrogen into helium in its core, a process that generates the immense energy we perceive as light and heat. But this cosmic fuel is not infinite. In about 5 billion years, our sun will exhaust its hydrogen supply. Its core will contract and heat up, igniting the helium it has accumulated, causing the sun to expand dramatically into a red giant. It will swell so large that it will engulf Mercury, Venus, and potentially even Earth. After this red giant phase, the sun will shed its outer layers, creating a beautiful glowing shroud of gas and dust known as a planetary nebula. This expelled material, enriched with heavier elements forged in the star's core, will eventually seed new generations of stars and planets. What will be left behind is the star's immensely hot, dense core, a white dwarf. The remnant core, now a white dwarf, is a far cry from its former glory. It possesses about half the mass of the original star, yet it's compressed into a volume no larger than Earth. This extreme compression is what leads to its astonishing density. Imagine squeezing the entire mass of the sun into a sphere roughly 7,500 miles in diameter. A single teaspoon of white dwarf material would weigh more than 5 tons on Earth. This incredible density is not due to gravity alone, but to a quantum mechanical phenomenon known as electron degeneracy pressure. In a normal star, gravity constantly tries to crush the star, while the outward pressure from nuclear fusion fights back. In a white dwarf, fusion has ceased. The atoms are so tightly packed that their electrons are forced into the lowest available energy states. These electrons resist being squeezed any closer, creating an outward pressure that perfectly balances the inward pull of gravity. This pressure is independent of temperature, meaning a white dwarf can remain stable even as it cools over billions of years. The initial temperature of a newly formed white dwarf can be scorching, exceeding 100,000 Kelvin, or about 180,000 degrees Fahrenheit. This intense heat causes them to glow brightly, emitting a white light, hence their name. However, they possess no internal energy source. They are stellar embers, slowly radiating away their residual heat into space. Over cosmic timescales, they cool and dim, eventually becoming cold, dark objects known as black dwarfs. These theoretical objects are the ultimate fate of all white dwarfs, but the universe is not yet old enough for any to have formed. The time required for a white dwarf to cool to black dwarf status is estimated to be trillions of years, far longer than the current age of the universe, which is approximately 13.8 billion years. So, all observed white dwarfs are still cooling embers, gradually fading from view. While white dwarfs themselves are stable remnants, they can participate in dramatic cosmic events, particularly when they exist in binary systems. If a white dwarf orbits a companion star closely enough, it can gravitationally strip material from its partner. This stolen hydrogen and helium gas accumulates on the white dwarf's surface, building up over time. As more material collects, the pressure and temperature on the white dwarf's surface increase. Eventually, this buildup can reach a critical point, triggering runaway nuclear fusion of the accumulated hydrogen. This sudden ignition causes a massive explosion, a nova. While a nova can be incredibly bright, it doesn't destroy the white dwarf. The explosion expels much of the accreted material, and the white dwarf itself survives, ready to potentially repeat the process if its companion star can supply more fuel. The most extreme fate for a white dwarf in a binary system occurs when the accumulated mass reaches a critical threshold known as the Chandrasekhar limit. This limit is approximately 1.4 times the mass of our Sun. If a white dwarf accretes enough material from its companion to surpass this limit, electron degeneracy pressure can no longer support its immense weight. Gravity overwhelms the outward pressure, and the white dwarf collapses catastrophically. This collapse triggers a sudden, complete ignition of carbon and oxygen within its core, leading to a Type Ia supernova. Unlike novae, which are surface explosions, Type Ia supernovae are the complete obliteration of the white dwarf. These explosions are incredibly luminous, outshining entire galaxies for a brief period. Because they occur when a white dwarf reaches a specific mass, Type Ia supernovae have a remarkably consistent peak brightness, making them invaluable standard candles for astronomers to measure vast cosmic distances and understand the expansion of the universe. Observing white dwarfs presents unique challenges. Because they are no longer producing energy through fusion and are steadily cooling, they become fainter over time. Detecting these dim objects requires sensitive telescopes and sophisticated observational techniques. Astronomers often identify them by their characteristic spectral signatures, the specific wavelengths of light they absorb or emit, which reveal their composition, primarily carbon and oxygen, and high surface temperature. Their small size also means they emit less light overall, making them harder to spot against the background of brighter stars and galaxies. Despite these difficulties, astronomers have cataloged thousands of white dwarfs within our Milky Way galaxy. Their discovery and study have been instrumental in developing our understanding of stellar evolution, the nature of matter under extreme conditions, and the ultimate fate of stars. White dwarfs are not just passive remnants, they are crucial cosmic factories. The material ejected during nova and supernova explosions enriches the interstellar medium with heavy elements like carbon, oxygen, and nitrogen, the very building blocks of planets and life. Our own solar system, including Earth and ourselves, is composed of elements forged in the hearts of stars that lived and died long before our Sun was born. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were once part of stars, processed and expelled into the cosmos by processes involving white dwarfs. They are, in essence, the recyclers of the universe, taking the ashes of dead stars and scattering the ingredients for new beginnings across the vast expanse of space. This ongoing cycle of stellar birth, life, death, and rebirth is a fundamental aspect of cosmic evolution. From the fiery end of stellar life emerges a dense, stable, and surprisingly influential object, the white dwarf. These stellar embers, supported by the quantum force of electron degeneracy pressure, are the most common stellar remnants in our galaxy. They are the silent witnesses to billions of years of cosmic history, the source of spectacular novae, and the trigger for universe-shaping supernovae. While they slowly fade into the darkness, their legacy endures, scattered across the cosmos in the very elements that make up worlds and life. The study of white dwarfs continues to reveal the intricate and awe-inspiring processes that govern the universe, reminding us that even in death, stars provide the essential ingredients for new beginnings.